Alright, before we start, if you are confused about anything from the last videos, go ahead and share your question in the comments. In this module, we will go over the process of determining the bias and slope or weights with gradient descent. In this video, we will review the cost surface, minimizing the cost surface in PyTorch via first principles. The cost surface. The cost is the average loss or total loss. Mathematically, the cost function looks like this. It is a function of the slope. The slope controls the relationship between x and y. The bias controls the horizontal offset. In true linear regression, the cost function is of two variables, the slope and bias. We can plot it as a surface. One axis represents the slope. The second axis represents the bias. The cost is the height. Let's do a simple example. With one sample, the loss is equivalent to the cost. The value for y is 1 and x is 1. This is the expression and plot of the cost function. For a slope value of 0 and bias of 15, we have the following point. Applying the cost function, we get a value of 256. In this example, we have a y value of 1 and an x value of 1. The loss or cost surface is given by applying the cost function. We get the following value of 361. At this point, the cost is so high. I think my model needs a loan. Okay, let's try to understand this better using contour plots. A contour plot is a useful tool for understanding cost surface. It's a bird's eye view of the surface as shown on the right. In this case, the parameter w corresponds to the horizontal axis, the parameter b is on the vertical axis. The contour lines represent two where the points are equal to a specific value. Imagine cutting the surface where the height is 200. It can be interpreted as a plane. The point where the surface intersects with the plane corresponds to the contours. Cutting the surface at a value of 400, this corresponds to the following contour. Similarly, a cut at 600 corresponds to the following contour. To get a better idea of how the contours work, let's take a vertical slice curve. For example, b equals 0. The resulting is a function of the slope. The curve should look like this. Let's look at the surface result from the following direction. The next curve is a horizontal slice of our surface and can be thought of as a function of w. We made the curvature a little more pronounced. Let's see what happens when we take some arbitrary cuts. The first slice corresponds to the first contour. We take the second slice 1 unit above. In this interval, the function is increasing fast. As a result, the corresponding contour line is relatively close. If we move another unit above, we see the function is increasing much more slowly. As a result, it takes a larger change in the horizontal direction to see the equivalent increase in the vertical direction. As a result, the contour line is much further from the second contour. We can see how different parameter values change the value of the cost. We simply overlay points in this graph. The following 3 points are different parameter values. We can see for each iteration the sample value is decreasing. Let's minimize the cost function in PyTorch. Just a note, there are several ways to do this in PyTorch, and you usually will not use the following method. We define the forward function. This time we add the bias. This is the equation of the line. We define the criterion function or cost function. To stay consistent with PyTorch documentation, we will sometimes refer to it as the loss. Let's initialize the tensors for the weight, bias, x and y values. The procedure is identical to the last video, except we also update the bias term. The following plot shows the loss or cost function for different values of the parameter. The red axis represents parameter values at a given iteration. The second plot shows the estimated function using the parameter values, and the red dots shows the training points. We performed 2 iterations or epochs. After 4 epochs, the value of the line gets closer to the data points. At 5 epochs, the line is approaching the data points. We see the parameter values are approaching the minimum. At 7 iterations, the line continues to get closer to the data points. Finally, by 15 iterations, the line does an excellent job at representing the data points. We can see the correspondence between the contour lines and the lost surface. In general, the derivative with respect to a multivariate function is called a partial derivative. If we put the partial derivative with respect to each variable into a vector, we get the gradient, hence the name gradient descent. The gradient is perpendicular to the contour lines and points to the direction of greatest change. The gradient also points to the direction of the next iteration. The same is true for the next iteration and so on. Thanks for spending your time with me. If you have any question or idea, drop a comment below.